We are approaching the halfway point. Not quite there yet, but we're on number 41. The quantum efficiency of a photon detector is 0.1. If 100 photons are sent into the detector, one after the other, the detector will detect photons, the average number of photons detected is going to equal 100 times 0.1. That's going to equal 10 photons. But quantum mechanics, we know, is probabilistic, so it's not always going to be 10 photons, just on average. And the binomial distribution standard deviation, we can apply that here, is going to equal the square root of the quantity np times the quantity 1 minus p. So where np is the mean and p is the probability of the event and n is the number of events. So the RMS would then be the quantity square root of 100 times 0.1 times the quantity 1 minus 0.1. Again, that whole quantity square root. So the RMS is going to equal 10 times 0.9, that quantity square root, and that's going to be the square root of 9, and that's simply 3 is going to be the RMS deviation, and the average detected photons is going to be 10, and so that is answer E. Number 42, two students perform an experiment in which they drop a ball from rest from a known height above the ground and measure the speed of the ball just before it strikes the ground. From repeated measurement, the students estimate the uncertainty in the measured speed of the ball to be 10%. Which of the following gives the uncertainty in the kinetic energy of the ball? Assume the uncertainty in the ball's mass is negligibly small. So we know the kinetic energy is going to equal 1/2 mv squared. So the kinetic energy Ke1 is going to be 1/2 mv squared, which is 1/2 m. Quantity, and 1.21 is 1.1. That'd be 1 plus 10%. 1.1 squared is 1.21. So 1.21 times v squared. Ke2 is going to be 1/2 m. And now let's do, instead of plus 0.1, let's do minus 0.1. So we're going to have 0.9 of the velocity. So 0.9 times 0.9 is 0.81. So 0.81 v squared. So Ke1 minus Ke2 equals 1.21 v squared minus 0.81 v squared is going to equal 0.4 mv squared. So the uncertainty in the kinetic energy is 0.4 mv squared, and so that is plus or minus 0.2 mv squared, and that is about 20% uncertainty in the kinetic energy. Answer D. 43. Which of the following wave functions represents a solution to the Schrödinger equation for an electron in the 2s state of a hydrogen atom? C is a constant, and AO is the Bohr radius. So one electron is radially symmetric, so there is no dependency on theta or phi. So answer B is the solution for n equals 1. That's the 1s state, and that's something we're going to just have to know, and you can see the diagram below, and so that only leaves answer C. 44. A particle in an infinite square well has its initial wave function an equal mixture of the first three orthonormal stationary states. Psi x of 0 equals the normalization constant A, psi 1 of x plus psi 2 of x plus psi 3 of x. The value of the normalization constant A is equal to which of the following? So the normalization condition means that the sum of the probabilities must equal 1. Each state is of equal mixture, as the problem states, so we're going to have a squared plus a squared plus a squared when you distribute that a to psi 1 of x, psi 2 of x, and psi 3 of x. So a squared plus a squared plus a squared has got to equal 1. And so 3a squared equals 1, and a simply equals 1 over the square root of 3. And that is answer A. Number 45. A matter wave of energy E is greater than 0, and wave number K is incident from the left on a potential well of width L and depth VO. The top of the well is at 0 energy, and the bottom of the well is at negative VO, as shown in the figure above. The spatial part of the wave function in region 3 has which of the following forms, and we are given that A is a constant. So the top of the well is 0 energy, and since E is greater than 0, E is also greater than V. So it has more VO rather, so it has more than enough energy to penetrate the barrier. If VO was greater than E, you would have quantum mechanical tunneling. So on the flip side, it would be equal to A e to the minus alpha x, where alpha equals the quantity 2m times the potential energy minus the kinetic energy, that quantity divided by h bar squared, and that whole quantity square root. So since E equals h bar squared, k squared over 2m, and because E is greater than V, i.e. V minus E is negative, minus alpha is proportional to minus k squared, that quantity square root, which equals ik, and we know that I squared equals minus 1, so that is going to simply be the positive version of what we would expect for quantum mechanical tunneling, and that is answer A, where the alpha now has a positive. Number 46. Spring 1 has force constant K1 and spring 2 has force constant K2, where K1 is greater than K2. If the same external force is applied to both springs, which of the following is true about the extensions delta x1 and delta x2 and the stored potential energies U1 and U2 of the two springs? So we know that the spring force F equals Kx, and so F1 is going to equal Kx, and we can say that because K2 is less than K1, we can just say that F of 2 equals 1/2 of Kx. So we're just using the simplest possible numbers here. So x1 is going to equal 1 meter, x2 equals 2 meters. So therefore, U is going to equal 1/2 kx squared, and U1 is going to equal 1/2 k of 1 meter. That quantity squared equals 1/2 of k. Again, units are somewhat left up to you to carry forward, so it doesn't muddle the math. And then U2 is going to equal 1/2 k times 2 squared equals k. So you can see that U2 is greater than U1, and the uncertainty in the extension of x1 is going to be less than the extension of x2, as you can see right here, and so that is answer A. 47. A stone is glued to the top of a light wooden block that floats in a pool of water as shown in figure 1 above. Assume that exactly 50% of the block is underwater and that the stone has half the weight of the block. If the block and the stone are flipped over, as shown in figure 2, and replaced in the pool, the amount of the block underwater will be. So the mass of the stone equals 1/2 the mass of the block. The buoyant force acts upwards, and objects underwater lose weight because of Archimedes' principle. The apparent loss of weight in water equals the weight of the object in air minus the weight of the object in the water. So the weight of the object in the water equals the weight of the object minus the weight of the displaced fluid. So, since weight is a force, so less would be submerged, and that is answer A. Number 48. A uniform solid disk starts from rest and rolls down an inclined plane without slipping. After some time, what fraction of the disk's total kinetic energy is rotational kinetic energy? So we know our potential energy is going to equal our kinetic energy plus our rotational kinetic energy. So mgh equals 1/2 mv squared plus 1/2 iw squared, where I is going to equal 1/2 mr squared and W is going to equal V over R. So our total kinetic energy is going to be 1/2 mv squared. That's our translational kinetic energy plus 1/2 of 1/2 mv squared. That's our rotational kinetic energy. That's going to equal 3/2 mv squared. Again, our total kinetic energy. So the rotational kinetic energy fraction is going to be, which is the 1/2 of 1/2 mv squared. So 1/4 mv squared divided by 3/4 mv squared equals 1/3 of the total kinetic energy. That's answer B. Number 49, two projectiles are launched from ground level with the same initial speed. The maximum height h1 reached by projectile 1 is twice the maximum height h2 reached by projectile 2 if theta 1 and theta 2 denote the respective launch angles as measured from the horizontal. These angles satisfy which of the following relationships? So mgh and mg2h are what we're interested in, where a of y, the acceleration of y, equals minus g, and a of x is going to equal 0. So again, we need to know our kinematic equations, where v of x equals vo cosine theta and v of y equals vo sine theta minus gt. 1/2 mvo squared equals 1/2 mvx squared plus v subscript x squared plus mgh, and h is going to equal vo squared divided by 2g, that quantity times 1 minus cosine squared of theta. And so sine squared of theta plus cosine squared of theta, we know, equals 1. Those are our trigonometric identities. So h is going to equal vo squared divided by 2g, that quantity times sine squared of theta. So 2h1 over h1 is therefore proportional to sine theta 1 squared divided by sine theta 2 squared equals 2. So therefore, sine theta 1 squared equals 2 times sine theta 2 squared, and sine theta 1 equals the square root of 2 times sine theta 2, and that is answer B. Number 50. When an object is located 25 centimeters from lens 1, an inverted image is produced 100 centimeters from the lens, as shown in figure 1 above. A second lens with a focal length of positive 20 centimeters is placed 110 centimeters from the first lens, as shown in figure 2 above. Which of the following is true of the image produced by lens 2? So 1 over do plus 1 over di is going to equal 1 over f, f being the focal length. And 1 over 25 plus 1 over 100 is going to equal 1 over 20, and that's going to equal 1 over f. So the focal length equals 20 centimeters. So since the object is outside of the focal length of the first convex lens, it's going to be inverted. And for double convex lenses, a virtual image is going to be produced. And so that is going to leave us with answer C. Okay, that's officially the halfway point. I will see you on the second half of the solutions.